gamma ray bursts are more concentrated than magnetar flares.
It's a concentrated beam of radiation, like a laser beam. It comes out as a narrow stream.
The gamma rays in the beams are also traveling much faster than the particles coming out of black hole jets.
The observations show that the energy is coming out in jets, moving at very close to the speed of light, 99.9999% the speed of light.
At that mind-bending speed, in just a few tenths of a second, short gamma ray bursts can release as much energy as our sun does in millions of years. But for years, scientists couldn't figure out why some gamma ray bursts were long, lasting many seconds or even minutes, while others were usually only a fraction of a second. Then, one burst in 2005 led researchers to an exciting new theory about incredibly dense neutron stars annihilating each other. The power of man-made atomic bombs is nothing compared to the galaxy-rattling explosions in the cosmos. As we continue counting down 10 of the biggest blasts in the universe, these cataclysmic events are now producing as much energy as our sun does in millions of years. Short gamma ray bursts are number 4. For years, scientists have been confident of the source of long gamma ray bursts, those that last over 2 seconds, and sometimes erupt for many minutes. They come from galaxies with massive stars. And when certain massive stars die, they collapse and then explode, blasting out incredible amounts of energy as concentrated jets of gamma rays. But in 2005, detectors in space captured a powerful gamma ray burst that only lasted for a fraction of a second.
This was very exciting because all the gamma ray bursts we'd seen before were of a different variety, longer, coming from galaxies where massive stars were dying. This was something different. It was short, and it came from a region where no massive stars existed.
This burst came from a galaxy thought to have some incredibly dense neutron stars in binary pairs that orbit each other. And scientists believe that the only way to generate such a quick and powerful burst of gamma rays is if 2 neutron stars engage in a deadly dance, orbiting closer and closer, then finally crashing into each other. This is thought to be the moment when a black hole is born.
When the 2 neutron stars finally touch, one of the neutron stars gets shredded into a disk, and the thing that's left is too big to be a neutron star. There's no force in the universe that can hold up 2 neutron stars, so it collapses to a black hole.
The 2005 event, known as GRB 050509b, since it was the second burst to occur on May 9th of that year, was the first short gamma ray burst whose location was pinned down. It didn't look very bright from Earth, but that's because it was an astounding 2.2 billion light years away.
GRB 0509b lasted only about 40 milliseconds, but in that time, it released about as much energy as the sun will release in 100 million years.
But the power of colliding stars can't compete with the even larger amount of energy released when an entire star explodes from the inside out. Number 3, supernovas. When large stars die, they don't just fizzle out like our sun eventually will. They go out with a bang. There are actually several types, but the two main ways a supernova explosion happens is either when one star in a binary star system swallows part or all of its companion, or when a supermassive star collapses in on itself and ejects its outer shell in the process. Either way, a mind-boggling amount of energy is quickly released.
The energy of motion, the kinetic energy of the ejected material, can equal the total amount of energy that the sun will release over its entire 10 billion year lifetime.
The binary star type of supernova is similar to a hydrogen bomb, where runaway nuclear fusion leads to a massive explosion. These are known as Type 1a supernovas, and in 2003, one of these blasts flooded the cosmos with more light than an entire galaxy of stars combined.
It was over 20 billion times more luminous than the sun for about 2 weeks. And this all came from the explosion of something not much bigger than the moon, about 1.4 times the mass of the sun, from a thermonuclear explosion from fusion.
For the core collapse type of supernova, an incredible amount of power is generated when the outer shell slams down and gets an extra kick from the denser core of the star.
Imagine this ping pong ball represents that outer, lighter material of the star, whereas this superball represents the heavy inner core. You can see that the ping pong ball actually doesn't really bounce that much on its own, and there's the bounce of the superball. But what you'll see is that when I send them down together, the bounce of the superball back up will propel the ping pong ball much higher. And that's very much like what happens in the supernova, where you have the heavy inner core bouncing back out and meeting that lighter material and blowing it out.
In fact, one supernova explosion in 2005, known as SN 2005 AP, flashed brighter than all of the others for weeks on end. But it didn't do any damage to Earth because, luckily, it was also 4.7 billion light-years away. And like many of the other blasts on the top 10 list, supernovas don't just destroy.
A supernova is a little bit like a recycling center. There's a lot of material in those massive stars. Anything from 8 times to over 100 times the mass of our sun. So there's a lot of material that's going to be processed in those stars, just like there's a lot of raw material here at the recycling center that's going to be processed.
The matter in the universe is dominated by light elements like hydrogen and helium. But the inside of a star about to go supernova is the main source of the various metals and other heavy elements we depend on for life.
Just like these materials are being sorted into different categories, the star starts to process heavier and heavier elements, starting with hydrogen, then helium, making heavier and heavier elements all the way up to iron when the fusion process stops. Later on in its life, when it becomes supernova, with the aid of the compression effects in the supernova, the star will make even heavier elements. Just as these materials are now